Hello everyone again. This is part 2 of Black Shear Strength. So let's demonstrate what we have learned from part 2 on this example here and understand the details on how things works out. So let's read the problem statement first. First it says in L angle 6 by 4 by half tensile member of A36 steel is connected by 3/7/8 of an inch bolts. I was showing in this figure on the side, which is 9.10, determine the strength of the member. So now we don't know if the member is going to fail due to tension or to black shear failures. So we're gonna test this out. If you look at the solution here, let me grab my pen again. You see here part 1, this is part 1, and this is part 2. So in part 1, we're gonna test out if it's going to fail by tension, what will happen, and if it's going to fail by black shear, what will happen. So for the first part here, as you can see, A is yielding in a gross area, and the second part is rupture in the net area. So we're gonna test this out and see. If you guys remember from previous lectures, we said we're gonna have to calculate the yielding in the gross area versus the rupture, and whichever is lower is the one that controls the failure that controls. Why? Because the lower or the smaller value going to fail first. They could fail in the same time, but our intention is to see which one is going to fail first, because we will have to design based on this. But for now, we're doing just analysis, so we want to understand which one going to fail first. Is it by rupture in that area, or is it yielding in the gross area? So first, to start with, we have to find the gross area, the A sub G. Now, for all these properties, the angle properties, you go to Appendix 6 by the end of the book, and you find all the values. For this example here, we don't have this size of an angle 6 by 4. This is big. The biggest I think we have in the appendix is 4 by 4 by 4, 4 by 3, and so forth with their thickness. But for now, if you like to find the gross area for this steel of angle, you just Google it. Just Google the properties of angle 6 by 4 by 2, and it gives you the gross area, which is 4.75 inch squared. Then the second step here is to find the hole size, which is H. So if you remember, we said for the bolt size 7 by 8, or any actually bolt size, we always add 1/8 of an inch to it to come up with the hole size, and this is what we did here. So we have the bolt size, we added 1/8 of an inch to it, and then we came up with 1 inch, which is the hole size. Now, from this equation, I believe if you go back also in the previous lectures, you will find the equation, which is PU equals 0.9 times Fy times AG. This is Fy, and this is AG from the equation. So then 0.9 times Fy, which is 36, it's already given here. And to find it, you go to table 9.1. The classification of the ASTM, it'll give you the Fy and Fu, but for now we have the Fy times the AG, which is 4.7, and it gives us 153.9 kips, and that's the PU for the yielding stress, for the yielding in the gross area. Now, let's calculate for the rupture now. We find the AN equals the AG minus 1 hole area. The AG is the gross area, times 1 hole, which is 1, times the hole size, which is 1, times half, which is the thickness of the plate. and this gives me 4.25 inch squared. Now for the U, that's the shear leg. Also, if you remember from previous lecture, if I want to take you back in the slides that we went over, I believe, right here, this point right here. For single or double angles with the 3 bolts in the direction of loading, U equals 0.6. And in our scenario here, in this example, we have 3 bolts in the area of the tension. So then our U is 0.6. Then the AE, which is the effective area, is U times AN. Well, we find both of them, 0.6 times 4.25, and this gives me the 2.55 inch squared. Now, to use the equation of the rupture, which is 0.75 times FU times A sub E. So this is FU, and this is area, effective area, or AE. 0.75, again, 58 from table 9.1, times the AE, which is the value that we just find, and then it gives us 110.9 kips. So then in comparison with the yielding in the gross area, the rupture is way smaller, which means it controls. So this case here, it fails by ruptures first. So now we identify the scenario that is going to fail by a rupture. Now we want to know how the black shear is going to work out in the scenario. And since we have, this is the tension, this is the shear, so we want to know how this is going to turn out to be. Now for the black shear, we have the AG sub V, which stands for the gross area along the shear surface. This is the gross area along the shear surface, which means here along this line AB. So we have 10, and that's the distance 442 from here to here. That's 10 times 0.5, which is the thickness of the plate from here. And the shear surface gives me 5 inch squared. Now, how about the net area along the AB? Net area is going to be the AGV minus 2.5 times the whole area. So 5 is what we find here, 5 minus 2.5 times 1, because it's 1 whole, times half, which is the thickness, and this gives me 3.75. Then, so as you can see here, we have step 1, A, B, C, D, and E, kind of steps to be able to work on these 2 equations that we talked about. So we have the net tensile area, which is 2.5 T, which is the thickness, minus half times 1 whole. Again, 2.5, just a plug-in chuck, times half minus half times 1 times half, which is the thickness, and this gives me 1. For the shear log, it's 1 here. How do we know? If I take you one slide back, U sub BS is 1 when the tensile stress is uniform. In our case, here is uniform. We'll cover something ununiform so you can compare. And then this takes us to the equation. The equation here is phi times 0.6 FU times A sub NV plus UBS times FU times ANT. Plug and chug from everything here we found, you come up with this value. The second equation is 0.6 times FY, not FU, AGV plus UBS times FU times ANT. Then again, a plug and chug from everything we find here, and that's your value here. Then we find that the strength, it's 110.9 kips which controls by rupture. So due to the strain of time, I'm gonna stop here.